So this is work done in collaboration with Rob Lazenby, who's in Perimeter. Okay, so these stellar cooling bounds are constraints you get on new light particles, and they come from many observations of many different astrophysical systems and apply to many different new light particle candidates. So for the sake of this talk, I'm not going to try to be encyclopedic and cover every single permutation or combination of astrophysical objects and new light particle candidates. Instead, I'm going to spend most of the time talking about dark photons. And in particular, the constraints you get from supernova. And this is going to be mostly because dark photons are the simplest case, so it's a lot cleaner just to go through the algebra on the board. After that, I'll very quickly show you some bounds from, well, other sorts of stars on vectors coupled to, on new vectors coupled to the standard model B minus L current, and also on new light scalars. So actually, I think these two cases are the most interesting ones, and they're the ones where we make the most new contribution. The dark photon is actually sufficiently simple that people had got the physics pretty much correct, although not for the supernova case. So we correct the supernova case, the old limits were just wrong, but most of the physics was pretty much understood by Redondo and people like that a while ago. Whereas for these cases, you need the full sort of formalism that we introduce. Okay, so despite having TV in the title of the workshop, I guess I don't need to motivate new light particles too strongly for people here. There's already been some nice introductions in previous talks. All I will say is that for me, these are one of the best motivated candidates for new physics. If you think from a UV perspective, then okay, there's a lot we don't know about string theory, but it's at least plausible that typical compactifications of string theory give you extra U1s, extra axions, extra hidden sectors. And then from a pheno perspective, if you have new light particles, they can be interesting dark matter candidates. These things can have interesting self-interactions, maybe resolving issues with small-scale structure. They could also be portals to more general dark sectors, yeah, all sorts of things. And there's also some sort of vague experimental anomalies, hints. I wouldn't necessarily take these things super seriously, but they're at least there. Also on a sociological perspective, compared to, say, collider physics, the physics of light particles has just been a lot less explored than many other things, which means there's important things to do, and constraints can really change by orders of magnitude, including relatively simple effects. On the other hand, if you again compare to sort of conventional solutions to the hierarchy problem, there's nothing quite analogous to the usual approach of just looking for, well, for the hierarchy problem, you look at the TV, you look at the electroweak scale for coloured particles. If you don't find anything there, you look at the TV scale, etc., etc. Whereas for the case of light particles, there's no kind of canonical place to look. The constraints or the parameter space spans many orders of magnitude, both in the mass and the coupling, and the physics in all of these regions can be quite different. So in some sense, this even makes theoretical input and understanding existing constraints from astrophysics or cosmology more important. If you're going to design new experiments, you want to understand what is being searched for, what models you're probing, maybe what model building you have to do in order to avoid cosmological constraints, and these sort of things. So that's where stellar cooling bounds come in. Okay, so the idea with these is we have some new light particle, let's call it X. So X, and it has some coupling to the visible sector. G, which we'll assume is small, otherwise it would have been ruled out being light. Now if we look at some star, then it will have some typical temperature T, and if T is bigger than roughly the mass of X, it's going to be possible to produce this new light state inside the stars. Because you're producing the new light state, you're going to change the dynamics of the star, and this is going to lead to what some people call cooling bounds, but really you should call anomalous energy transport. The effect this has depends actually on how big G is. So if G is really, really small, then if your star roughly looks like that, you produce your new light state, and it will simply escape off to infinity. So no matter where in the star you produce it, it just takes energy out of the system. So I'll call that volume emission, and that's for very weak coupling. On the other hand, suppose we have slightly stronger, or still very small but slightly larger G. The picture is going to be that we produce X somewhere inside, it moves some short distance, gets reabsorbed, will get emitted again, reabsorbed, and eventually get out of the system this way. So in this case, we're still changing the dynamics of the system, but in a much more subtle way. Here it's contributing to the heat transport rather than just removing energy from the system. And this you can call okay.
Does it matter whether or not it eventually escapes?
So you have to sort of it's a question of
effect?
How big the effect is. Generally it escapes in the end. By the time emission stops being efficient, usually the absorption is also sufficiently inefficient that it won't get absorbed again. And we want to place constraints on a new light particle by saying that the dynamics of the star is going to be changed. So the way you do that, or the way you hope to do that, is by looking at systems where the standard model energy loss is inefficient. This means that even for a relatively small coupling G, we're going to change the dynamics reasonably significantly. So, inefficient standard model is, state the obvious, good. Luckily, there are plenty of systems in the universe or in astrophysics where standard model emission is not particularly efficient. So if you're looking at some system which cools by emitting neutrinos, this is not a very good way of taking energy out of the system. The neutrinos are not very strongly coupled, so they don't get emitted particularly fast. Also, if you're looking at some star which loses energy by emitting photons from the surface, this is also not taking a lot of energy out of the system, well, at least compared to the photons were emitted in the core, just because the surface is at much lower temperature. And to give you some idea of the sort of systems or the parameter ranges that we are going to be sensitive to, I will just list a few of the main ones, the most important ones. So first of all, we have the Sun. This has a temperature of about, let's see, roughly keV, that will do. Then we have red giants before they start burning helium. These have slightly higher temperature, 10 keV. And horizontal branch stars, also about 10 keV. And finally supernova, which are much hotter at about 40 MeV. And okay, just as an illustration, I'll also list the density, which is in grams per centimeter cubed. 50. 6. And supernova are much denser, 10 to the 14. And finally, the important thing for us is the maximum energy loss that's allowed before you disrupt at least in the weak coupling case, what the maximum energy loss that is allowed before you disrupt the system. So this is in ergs per gram per second. 0.2. Sorry. Yeah. You write a mathematical file that converts these things into sensible units, and then you never worry again. 10 to the 14. So in these cases, the dynamics is known pretty well, and your new energy loss, in this case, can only be like 10% of the standard model energy loss. In these cases, it's like order of magnitude. Whereas in this case, the dynamics are known much more poorly, but the temperature is much higher. So you can really emit a lot of new energy before you disrupt the neutrino burst. And indeed, the constraints here come from, for the supernova, if you emit too much energy, then you don't get enough energy emitted in neutrinos. And given that we've seen supernova events with a significant neutrino flux, this would be in contradiction to observations. Okay. So that's the kind of introduction. Now, suppose you want to actually calculate these things. There are three important steps, I guess. First of all, you want to calculate the production rate of X, your new light state. Then you have to put this into the dynamics of the system. And then finally, you compare to your observations. And by far the most interesting one from a sort of QFT point of view or from a theoretical point of view is this first bit. This is a case of going off and finding, for example, models of stellar structure that other people have implemented. And then this is a case of comparing to observational data which other people have taken. So our new contribution is really on this part here. Now, the first thing you try if you want to calculate this is you think about the processes that might lead to the emission of X, decide which one is parametrically dominant, and just calculate some diagram that looks, I don't know, maybe something like this. So here, A is going to be the standard model photon, and you could have some electron-proton scattering, say. And our new state, X, getting emitted. And okay, if you're just doing this initially, probably you're going to calculate the vacuum matrix element for this, and then put in thermal abundances for the initial and the final states, and say this is job done. This is superficially reasonable, but after a bit of thought or a bit of time, you might start noticing the rates are not behaving the way you expect in certain limits. And then the next thing to worry about is you might also have diagrams, or you might be working in a not particularly good basis even in the vacuum. So you might have diagrams that look like minus, still standard model photon, same stuff there. But now you produce the standard model photon A, and then you have some in-vacuum mixing between the photon and our new state X. So these sort of diagrams will turn up and matter if your vacuum propagating eigenstates are not the same things as your basis or your choice of basis. Okay, unfortunately for stellar cooling bounds, this is still not quite right. So the things that are getting missed here and the things that we point out are diagrams that look like E minus, produce a standard model photon, then produce X, that's still A. These sort of diagrams where this circle is supposed to represent full sort of thermal effects and all the stuff that is going on because now you're calculating production rates in a star, in some thermal bath, not just in the vacuum. And
particular system one?
No, so because you've broken Lorentz symmetry, it will also matter for scalars. Scalars can mix into the standard model photon. For fermions, it probably doesn't matter because just there's no low energy fermions in the standard model. No, in the standard model at low energy, there's no fermions. I'll show you the scalar case quickly at the end. Yeah, maybe.
Is that not low enough?
I think the mixing would never be significant. We did some estimates, and probably the mixing's never going to be significant, even in supernova.
Difference between the second and the third diagram because essentially they do not look too different from one another.
So this is only supposed to mean that this is what you would calculate if you forgot everything was in a thermal bath.
So this is just vacuum data?
Yep. And then in the thermal medium, really if you calculate everything, you do them both at once. It's not as if you separate them out, but just for illustration.
Because in the thermal bath essentially you will not always be able, at least technically, distinguish it in the second.
No, yeah. Conceptually there's no split, it's just, for a long time people calculated these things only including these first two by effectively calculating everything in vacuum. And I agree it's not a clean split.
Are there any effects when you scatter off the exchange A multiple times and the time it takes to emit an X? Some processes in finer temperature, there's an enhancement, I think, in the forward direction.
Yeah, so this would correspond to sort of, I guess, using full thermal propagators for the states on the legs, or for the internal states.
Some kind of ladder.
Yeah, so I guess morally that would look something like that.
A reflux.
He means like a box turns into a ladder with many rungs.
Okay.
In QCD they do that in people.
Yeah. Maybe, potentially. Yep.
So one more question, I'm not sure, are you making an assumption that chi also thermalizes there, or because A is for sure thermalizes, whether chi thermalizes, or your calculation doesn't care about it?
It doesn't need to thermalize, no. It doesn't care about this. Maybe this will be clearer from the calculation rather than the diagrams. Yeah, I didn't think about those, but maybe. And okay, the reason you can't get rid of these diagrams, or you can't just make this a trivial problem, is that typically there's no one good basis for all frequencies where you can diagonalize this away. There'll be different mixings for different frequencies, and it's better just to deal with this once and for all rather than trying to get rid of it somehow. Okay, one reasonable question at this point might be, particularly for the supernova, where there's order of magnitude uncertainties, why should I care about these relatively small corrections? If it's just going to be loop factors, then why bother? So I guess the answer to that is that it's not just loop factors. And just to make this argument in a kind of hand-wavy way before it becomes a bit more precise, I can show you or plot the dispersion relation in, let's say, supernova. So this is frequency in, say, MEV against momentum in MEV as well. And my light cone looks something like that. My new light state has some mx, has a dispersion relation which looks like this. Now, because we're working in a medium, the photon effectively gets a thermal mass or gets a non-trivial dispersion relation. And in particular, for the transverse degree of freedom of the photon, this looks just like some fixed mass. And the mass is set by something that is parametrically called the plasma frequency. So omega p is, roughly speaking, alpha EM. Okay, let's put pi's in it. 3 pi 4. Where T is the temperature, mu is the chemical potential of the electrons. And its dispersion relation then looks something like this. So that's the transverse degree of freedom of the photon. Since I've broken Lorentz symmetry in my plasma, there's also an excitation that I can identify with the longitudinal degree of freedom of the photon. And this thing has a really unusual dispersion relation. So it crosses the light cone, it looks something, it goes up a little bit, but pretty much flat. So that is a longitudinal degree of freedom. Now you can see that something potentially interesting happens here. Sorry, thank you. So you can see there's the potential for something interesting to happen here. Because the longitudinal degree of freedom crosses the light cone, anytime the mass of the new light state is below the plasma frequency, there will be some point where these two intersect. And at this frequency, let's call that resonant L, these sort of diagrams become very efficient. So they become parametrically much more efficient than you'd expect from just perturbation theory. You can also get situations where if, well, the plasma frequency is actually a function of the location in the star, because it's a function of the chemical potential and the temperature, this is varying throughout the star. So there will be some particular regions where the plasma frequency and the mass of the new light state coincide. At that point, the two dispersion relations for the transverse photon and for the new particle overlap everywhere. So this means that you get very efficient resonant production effectively for all momentum. And these sort of regions where this happens will emit lots and lots of energy in the new light state. Okay. So that's the sort of hand-wavy motivation that things might matter, or things that at least it's worth trying. Now we can do, it's not actually too much harder to just do things precisely, or to actually calculate things. So, okay. So the thing you want to calculate effectively is what are the propagating degrees of freedom in my medium. The problem that I've just rubbed off was that the degree of freedom that I thought was x was not actually the proper degree of freedom that was being emitted. And the way you do that is you have to find the null eigenvectors of some matrix. This matrix is, I'll write it down and then describe it. A squared minus pi a plus pi a x minus pi xa a squared minus pi. Okay, so I'm assuming my new light state is bosonic and that it is neutral under the electromagnetism. So the thing it's going to be mixing with is the standard model photon. This k here is the usual energy momentum for vector, so omega k. And then these pi's are the self-energies calculated within thermal field theory. Now the parts of the pi's that we care about are effectively the things giving mixing between the hidden and the visible sector. This means that the off-diagonal parts and this part are small in our small coupling. So we have that pi ax goes as g, pi xx goes as g squared. And as a result, we can immediately diagonalize or find the null eigenvectors of this thing and find what the weakly coupled degree of freedom is, or what its dispersion relation is. So it turns out we have omega squared is a squared plus x squared plus pi xx a squared. Okay, so this is the dispersion relation of the thing that is mostly like x. plus order g to the 4. And the final bit of thermal field theory I'm going to assume, or just claim, is that the production rate for the new light state is related to the imaginary part of the self-energy of the propagating state. Maybe this is kind of, well, I guess it's familiar from normal Q of t, and it's kind of standard in thermal Q of t. So this means that production rate per unit volume, per unit time, goes as integral d cubed k, drop some pi's and things, 1 over omega. FB is just some thermal occupation number distribution, it doesn't matter. Okay, so to calculate our production rate, we just need to calculate this imaginary part here. This first term will correspond to the diagrams just producing x directly off the legs, and everything in this second term is what's dealing with the mixing. So whenever pi xa is non-zero, there's going to be mixing effects. That's pretty much all the formalism I need, so now we can just go straight to dark photons and calculate this thing. This off. So this is the bosonic thermal occupation number in equilibrium.
Don't you need your cross-section for electron-proton scattering?
That will come into the imaginary part of pi xx. Yeah, so you have to calculate these things, and you do that just by writing down all the possible processes and just doing the calculation.
Where do you get your electron and proton distribution functions from? The occupation?
This is this will be the thermal occupation number. The star is close enough to equilibrium that this is a good approximation. Yeah, that's a lot of the actual time is spent calculating these things carefully, but okay, it's kind of an exercise in reading Landau and Lifshitz carefully and working out what the most important production mechanisms are. So, Lagrangian for dark photons is just the usual, minus 1/4, some new U1 squared, give it a mass. It doesn't matter how the mass turns up. It could be Stuckelberg or some Higgs. And also couple it to the standard model electromagnetic current, EM. Gx. So G is the small coupling to the electromagnetic current. And this could be generated, for example, by new heavy states coupled on, well, charged under the visible sector U1 and also the hidden sector U1. Factors right. Okay, this has, well, the reason the dark photon case is simple is that all the self-energies can be related to the self-energy of the photon in a very direct way. So we have pi xx is exactly equal to g squared pi aa, and pi xa is g pi This is just because all the interactions of the dark photon are the same as of the visible sector photon, but with extra factors of g. As a result, the important thing we need to calculate, which is this, simplifies down nicely. And, okay, let's just...
So you're doing the masses in that statement?
Sorry?
The dark photon has a mass, So it's the same as the standard model photon.
So... So what's this? So, okay, to leading order, this is true. To higher order, you have to worry about the masses.
So this is some expansion of the mass.
Yeah. No, more an expansion in perturbation theory that because the diagrams will look something like, okay, so we have, it's mostly going to be generated by electrons, so it's going to be things like XA with, say, a loop of electrons. To leading order in perturbation theory, the mass of the dark photon won't matter. Yeah, I agree, to higher order, it might matter. So, because of this nice relation, our important thing, which is this imaginary part, reduces down to, well, just the imaginary part of G squared, M squared, you can reduce it down to get just this simple thing, which is the self-energy of the photon. And immediately this has some slightly reassuring features compared to if you ignored the mixing. So in the limit where the mass of the dark photon goes heavy, this mx cancels out and you just get back to the naive production rate, which is g squared times the production rate of the photon. And indeed this is what you expect if you're much heavier masses or much higher energies than the typical energies of your plasma frequency or the typical excitations of your plasma, then you don't expect thermal effects to do anything interesting. On the other hand, when you take the mass of X very small, this of course gets dominated just by, well, the denominator, and the whole thing vanishes just as you take mx 0. And this is exactly what you expect. You know that your original Lagrangian can be diagonalized in the case where mx goes to 0. You can actually redefine away your dark photon. So the two sectors should completely decouple. There should be no production rate from the standard model thermal bath. And indeed, the mixing effect means that this happens. Whereas if you'd included only the pi xx part of the production rate here, you would totally miss that. Okay, you can now further simplify this so that just split the self-energy up into real and imaginary parts, so that we have g squared mx to the 4, pi I is the imaginary part, pi I squared plus all squared. So that's just a trivial rewriting. This thing you have to calculate by deciding working out which processes actually produce your standard model photons. This thing is, well, the real part of the self-energy. You again just calculate in the medium. For a photon, you just calculate this thing. It's kind of known, and then you go off and put everything together. So there's actually 4 kind of, well, slightly conceptually different contributions here. Let's go onto this board, if this is visible. So first of all, we can have production of transverse photons or production of longitudinal photons. And then within each of these, we also have resonant production and continuum production. Continuum production. So resonant production is what happens when, well, typically this part of the fraction is just dominated by this part. So the real part of the self-energy is usually much bigger than the imaginary part. And when this dominates, okay, this is what I'll call continuum production. However, there are also special points or special frequencies where this part of the fraction, well, this term vanishes. And when that happens, this is what I'll call resonant production. So the points where this vanish are actually exactly the points I showed on the dispersion relation, when you get a matching between the dispersion relation of the new particle and the standard model photon, this thing vanishes, you get very efficient production, which is resonance. Okay, so maybe rather than going through the details, I'll just show you the results in practice. So I'm not sure how to turn this on.
Connect one of these cables.
Okay.
Down screen. Niki, can you turn off the front lights? Just try. Invert. Thanks.
Okay, that worked. Okay, so this is for supernova. Here you have mass of the new dark photon in MEV, our small coupling G. These are the constraints from stars. This slight curve up here is the effect of trapping. So this is if G is too large, it doesn't efficiently transport enough energy out of the system. Then we have constraints from cosmological bounds, things like decays to photons, which turn off very sharply at twice the electron mass. So if you're above the mass of 2 electrons, you can decay very fast to that, and then you don't get strong cosmological bounds. And we also have beam dump experiments here. And then in shaded black is the supernova bounds we find, including all the plasma effects. The 4 different contributions are shown in different colors here. So here is resonant transverse production. Up here we have, it's dominated by resonant production of longitudinal photons. And then up here it's continuum production. Then the dashed black line is the results you would get if you included only or if you didn't include the mixing effects that we're talking about, or that we discuss. And these are beam dump experiments. Okay, so I guess the things to point out here are that we indeed see a fall off at low masses, as you expect from the fact that the two sectors decouple. You also get a bit of an enhancement of the bounds just in this region, which is around the plasma frequency. And you lose a bit of sensitivity down here. So, okay, this axis is on a reasonably sort of large scale. So you're changing your bounds by a couple of orders of magnitude, which is worthwhile. It's not spectacular, but...
So where are the bounds before you?
Pretty much this dashed curve. So this is because you got the low mass behavior wrong and you missed the resonance. And then at high masses where it decouples from the plasma, it all agrees.
So I assume the upper edge of the region is kink at around 1 MeV. That's just because that's where the channel 2 electrons opens up,
Yeah.
and so the dark photons decay more efficiently.
Yeah, precisely, yeah. So probably this upper bound, talking to supernova experts, they think we're being a bit strict on this upper bound, and actually you would disrupt the system even up here, but we're not knowledgeable enough about supernova to really confidently exclude that region.
So you're really requiring that it gets all the way out of the supernova?
We're requiring that enough energy gets out. It doesn't have to be each individual one, but 10 to the 14 ergs per gram per centimeter cubed should get out.
But you're putting your new physics on a background of standard model physics, right?
Yes, exactly.
Because, I mean, for the axions, they actually redid it and included the axion in the full supernova simulation, right?
Yeah, roughly. Not in quite. I think the latest ones were not in the state-of-the-art supernova simulations.
Well, no, okay.
And then there's some.
Moved on, yeah.
Yeah, and I think even at the time when they put it in, the simulations were having problems getting explosions to happen at all. So.
Well, that had nothing to do with the axions.
No, sure, no. There was problems already with the simulations,
Yeah.
and at that stage, it's unclear how much you can trust the bounds you get from putting the axion on top of something.
I mean, you're assuming that your system is in thermal equilibrium. Is that true for a supernova?
So,
I mean, it's a dynamic exploding system. It has a temperature distribution and radius. And that's why they
yeah.
include the axion in the whole simulation to get the proper bound.
I fully agree. These bounds could change by sort of maybe even an order of magnitude. Yeah, I agree. That's another reason this is not the most exciting of our results, I don't think, is that, yeah, I agree. There's big uncertainties on supernova. Really,
The main effect is this lower triangle down here.
Yep, and I guess even for us, it was more the conceptual issue that the scaling was just not agreeing with what we knew it should be.
So in principle, how far does this plot extend to lower masses? I mean, in your case, at some point, now it goes to
So I
large
guess
particles, but in the old result, how far did they?
I think
Stops at 0.1.
it's once you get in the star bounds are more robust. So I mean, in principle, they would have seen it go down to 0 mass, but there was no.
Stay that strong? I thought the other bounds also go away at some point.
So the people had got the star bounds right in the low mass limit. So maybe those are the ones that. Yeah.
So it really doesn't matter.
Okay, so that's kind of the simple case where you can test the formalism and check that you understand what's going on. Now, very quickly, no, may as well leave it on. It's only
The stars here come from stuff like the sun, or?
these are horizontal branch stars dominantly. The sun kicks in at slightly lower masses just because of the temperature. Actually, I can already skip to the results for B minus L vector. So the Lagrangian here is pretty much what you'd expect. It's just now coupling x to j B minus L. And again with some mass. So if we're thinking about an environment with no neutrons, then at leading order, a B minus L vector will behave just like a dark photon. The charges of protons and electrons are the same as for the dark photon. And then also it turns out that when you do your calculations, the dominant production processes in stars are coming from electrons. This means that the dominant part of your bounds, which is all of this stuff down here, is effectively behaving like a dark photon. So we have exactly the same dynamics. We have some resonance region here where there's a coincidence between the typical plasma frequency of the sun, which is say 10 or 100 eV, and the mass of the B minus L vector. Then we get some turning off or some suppression at low masses because, well, including just the electrons, the B minus L vector should be behaving just like a dark photon. Until finally you get a bit of a constraint from neutrons. So unlike the dark photon, you still get some bounds as you go to small masses, just because the neutrons are still emitting B minus L vectors, whereas these things are not. So the decoupling between the two sectors isn't perfect in the small mass limit. And this bound, okay, this is what you'd get, not including our effects. So again, you get a bit of a triangle here, get a bit of an enhancement from resonance, and then up here we have trapping, then cosmological bounds. Okay, final case, which I'll just very quickly show you, is a scalar. So in this case, as I said earlier, the mixing is, I'll try to get the factors correct here, is with the longitudinal degree of freedom of the photon. In particular, if we have some Lagrangian, which includes some coupling of the new scalar phi to fermions, E phi fermion, phi f bar f. This induces mixing between phi and the longitudinal degree of the photon, which looks like phi, let's get this correct, A longitudinal, G phi f over E q f k over k squared. Self-energy of the photon. Okay, so here G is the coupling, E is electromagnetic coupling, QF is the charge of the fermion that's the new scalar is mixing with, is coupling with. K is momentum, K squared is the usual energy momentum 4 vector, and pi L is the self-energy of the longitudinal degree of freedom of the photon. Okay, and maybe just skipping straight to the production rate. Because of this mixing, you calculate your production rate, go through all the details, and it turns out for a frequency omega phi, you have G squared over E squared omega over all's good. Okay, so I won't explain the symbols or everything in detail here, other than to say omega is the frequency, this is the production rate, that's the coupling, and then sigma L is effectively the production rate of the longitudinal degree of freedom of the photon. So the structure is very similar to the dark photon. You have this part which usually dominates, and then you also have special frequencies where you get resonant production. You go away, you calculate this all for your systems, in this case we did stars, find the constraints, and it turns out that for red giants, or for stars in general, the resonant production dominates. This means that, and indeed, actually in this case, the emission rate, or the energy that gets emitted, is independent of the mass of the new scalar. Whereas in the dark photon case, it got suppressed. Here, it just because of the way the factors work out, it doesn't, which means that your constraints extend down to small masses. Okay, and these are the results we find. If you hadn't included the mixing, you would get effectively this bound here. Including these thermal effects, we get down to here, which is a factor of about 1.5 orders of magnitude in sine theta. So here I've parameterized the coupling as some mixing with the Higgs given by sine theta. And then these are cosmological bounds, force bounds. So between somewhere like 1 electron volt to about 10 keV, we win compared to all the other constraints. And again, okay, maybe from this plot it doesn't look like a big strengthening of bounds, but actually if you're building some new experiment or you're considering some new scalar which is living in this region, then, which actually experiments are doing, you probably should worry about this constraint and yeah, think about what sort of models are getting probed. Okay, so I think that's all I want to say.
Probably a naive question. What's the difference between the horizontal branch star and the red giant star? I thought the red giants were on the horizontal branch.
So this is just naming convention. Red giants are before for me, red giant is before it starts burning helium. So when it's cooling by neutrino emission. Then horizontal branch is when you disrupt the actual burning process of. Okay, so just to conclude, hopefully I've convinced you that, well, stellar cooling bounds give strong constraints on new light particles. Over large parts of parameter space, these are in fact the dominant constraint. And if you want to calculate these things accurately, which means orders of magnitude or even parametrics, you need to make sure to do your calculations reasonably carefully, including mixing effects. And okay, even though I've talked about stellar constraints, these sort of effects might also matter for early universe cosmology. So if you're thinking about the early universe, this is some hot dense plasma. The same sort of effects might matter here, and it would be interesting, well, it's work in progress to see if things like resonant production will also have significant effects in these environments and on the bounds that you get out then. So that's it, thank you.
So, do we have more questions?
Yeah. So presumably on your dark photon plot, you can draw a line below which it would escape the new particle would escape the star.
Yep.
And above which it doesn't. Do you know where such line would lie relative to your exclusion?
So this is, maybe I skipped past it, this is almost exactly this line. So the upper bound comes from if you don't get enough energy out to disrupt the system. And this happens basically when order one of the photons get reabsorbed.
And also to follow up with Pedro's question, so I've seen stellar cooling bounds for sort of EV or sub-EV dark photons. Does your work have any indications on?
Yes, but because the dark photon case is simple enough, people had got these basically right, so we didn't redo them. Whereas the supernova case was wrong, so we redid it.
But you looked into the possibility that this region just above your upper line, this could actually contribute to the supernova exploding. And if you produce these things in the core and then dump the energy at a few hundred kilometers, so that might be the kick that the supernova needs to explode.
So I sort of vaguely thought of this when I saw papers about dark matter helping supernova explosions, but we haven't tried it yet. It would be interesting if someone did, or if someone could do.
To really assess it is to implement it in the supernova simulation.
This is always the problem with the supernova, yeah.
So what's the general assumption? Is that the simulations are too stupid to make the supernova explode?
Well, we see that supernova explodes, and the supernovae are not too stupid. So.
Yes, some comment.
The general assumption is that there is, well, obviously something's missing. Either the simulations are getting the energy deposition by neutrinos wrong. That could be because they cannot fully implement the physics of neutrino oscillations yet. There are certain turbulent effects that are difficult to incorporate because you need a full 3D simulation to get them right. So it's quite possible that there is something we still don't understand at the supernova in the simulation side. Of course, there's also the possibility that there's new physics.
But there was also, they went from 1 to 3D or something. I mean, there were turbulence effects that were not present in 1D. My understanding was that Thomas Janka from Munich, Garching, that he got it to explode last
Well,
year.
they can get supernovae to explode, but there are some, let's call them fudge factors.
Yeah, it's slightly worrying that you have to work to make your supernova explode.
There are some things that you cannot compute from first principles yet. So you can adjust certain parameters in such a way that the supernova explodes.
So these bounds are much less robust than the stellar cooling ones, for example, where we really understand the models.
I'm not sure how important it is, maybe it's completely unimportant, but did you take into account, or you shouldn't even take into account the effects of the magnetic fields in the supernova? Supernova, even I don't know how it happens in stars, at least. Problems and better.
So, okay, the case this would really matter is for the axion, where because the axions are pseudoscalar, you could get mixing. Our estimates were that, fortunately or unfortunately, depending on whether you want to write another paper, even in supernova, the magnetic fields won't be big enough to give significant axion scalar mixing.
What are the magnetic fields in supernova?
Numbers I forget.
How do we know about?
Just make up a number and then
It's being video recorded. One person may one day watch it, and then they're big but not big enough, I think, is that all I can say without checking. We did back of the envelope calculations, and it was orders of magnitude off really mattering, so we stopped.
Okay, so everyone happy? Let's thank Ed again.